After last week's adventure in techniques of integration, that was a lot of fun. We've got to go back to thinking about how we think about education, how we think about integration. And we're going to start with these two problems. These two problems represent what I try to get across with what integration is about. In the first problem, a rod is 10 centimeters long and has a density of 2 grams per centimeter. Find the mass of the rod. In this case, normally density is, we normally think about density as mass per unit volume. But really density just says how much is there and how much space does it take up. So we can have a linear density. We don't care what the shape of the rod is. The density is all going in one direction anyway. If we have 1 centimeter of this, it's going to be 2 grams. And when we have 10 centimeters of this rod, it's 20 grams. We get there just by multiplying. And the units even tell us what we're supposed to do. I want to find a mass in grams. I've got grams divided by centimeters, and I've got centimeters. If I multiply those two, the centimeters will cancel out. So what we do is we just take the density, 2 grams per centimeter, and multiply it by the length, 10 centimeters, and get 20 grams. In this case, mass was just density times length. We didn't even have to think about what to do. We just kind of knew mass is density times length. What we want to notice, because this is calculus class, is that we got to multiply because everything was constant. In particular, the density was constant throughout the entire length. We get to multiply because density is constant. We get to multiply because the density was constant. And so that is the thing that changes in the next problem. Here we have another rod, which is 10 centimeters long, and the density of the rod at any point x centimeters from one end is given by 1 plus 0.4x grams per centimeter. So what changes is that the density of the rod is now variable. I want to calculate mass as density times length, but the density is variable. That's the change. Now that the density is variable, we don't get to multiply. Now we know that we're in a Cal 2 class and the point is going to be largely focused on integration. So we'll probably just integrate this function from 1 to 10, and that's exactly what we'll do. But we want to realize what that is based on. We want to do multiplication of density times length. So we assume that the density is constant for some small change in the length. So we know that we're going to calculate the mass is going we know that the mass of the rod is going to be the integral from 0 to 10 of 1 plus 0.4x dx. And we can even calculate what that is. Since we're not focused on techniques, we could just use a calculating machine, and we'll math 9 1 plus 0.4x with respect to x from 0 to 10. And we get a mass of 30 grams. Since density is variable, we integrate. We get to multiply if the density is constant, but since the density is variable, we have to integrate. In this case, we specifically integrate the density over the length. Well, we want to remember what goes into this integration. What we're doing is we're going to assume that the density is constant for some small change in the length, and then add up all of then we can multiply, then we add up all the masses. So the story behind the 1 plus 0.4x dx So our strategy is to assume that the variable thing is constant, but only for some small change. So we assume that the density is constant, and we give it the value of 1 plus 0.4x evaluated at some point xi for some small change in length, that's the delta x, so that we can multiply. Then we add up all of the values of all the segments. And then we do the calculus thing and let the number of segments go to infinity. We can think of integration as multiplication, but one of the factors is continuously variable. We model our continuous sum with a discrete sum and say that the continuous sum is the limit as the number of terms that is discrete sum goes to infinity. A picture of what's going on in this rod is we're imagining our rod that's 10 centimeters long. And at a point, xi units from one end of the rod there's our density of 1 plus 0.4 xi. We pick a fixed value of x, evaluate the density. So when xi is equal to 5, the density is 1 and 0.4 times 5. And then we use that density for some small change in x. And this is all based on the multiplication. Mass is going to be density times length. Any questions? Oh, this is not the one I wanted to go to next. Let's suppose we have a rectangle, 3 centimeters by 5 centimeters. And I'm going to put it in coordinates just because I'm going to do that anyway. Let's suppose we got a rectangle, 3 centimeters by 5 centimeters. It's in the first quadrant. Let's suppose that the density of this rectangle is 2 grams per square centimeter. Notice that I have an area. So my density is going to be mass per unit area. This problem is just the original problem with one extra dimension. As a character, that means there's no extra dimensions because it's the same thing. That's just how we perceive it. So it's not dimension in character, it's just dimension, length, and width. And we want to do the same thing. We want to multiply. Density is Mass is going to be, I had like two sentences that were fighting for supremacy, and it came out a stalemate. Mass is density multiplied by area. In this case, we get to multiply because the density is constant throughout the area. We get to multiply since density is constant throughout the area. So the mass is just going to be 2 grams per centimeter squared times the area, which is going to be length times width. Any questions? So, you know what I'm going to do next. I'm going to make the density vary. Then I'm going to make a couple of things vary. So let's consider that same rectangle. Same rectangle, 3 centimeters by 5 centimeters, sitting in the first quadrant. But now the density at any point, x units from the y-axis, but now we're going to have a variable density. The density at any point, x units from the y-axis is 1 plus 0.4 times x. So at any point, x units the density is 1 plus 0.4 xi. And we're going to do the same thing. Now, this is the density all along that vertical piece of the rectangle. That's the density all the way up and down this rectangle. And I'm going to use that density, whatever it happens to be, 1 plus 0.4 times xi, and I'm going to use it for some small change in x. Now that I'm going to assume that the density is constant for some small change in x, I'm going to use that density, whatever it happens to be, 1 plus 0.4 times xi, and I'm going to use it for some small change in x. And I'm going to use that density, whatever it happens to be, 1 plus 0.4 times xi, and I'm going to use it for some small change in x. Now that I'm going to assume that the density is constant for some small change in x, Now I get to multiply. Mass is equal to density multiplied by area. So now that the density is constant, I get to use multiplication. The density at this point is 1 plus 0.4 xi, and the area is length 3 times the width delta x. So the 1.04 xi is the density, and the 3 dx, the 3 delta x, is the area. Then we just add up all of the masses of these little rectangular strips, and that becomes our definite integral. So we take all of our masses, 3 times 1.1 plus 0.4 xi times delta x. We add up all the masses of these strips, and then we let the number of strips go to infinity. This Riemann sum becomes our definite integral. Our xi becomes a continuous x, our discrete delta x becomes a continuous dx, and we integrate over all the appropriate x values. That goes from 0 to 5. Questions? Notice the 3 parts that we have going on here. We've got mass is density times area, and I broke the area into length times width. So I've got the density. Here's the density. And the area is broken into length times width. So the area is the length times the width. Questions? Remember how this game works. We want to multiply constants. If everything is constant, we get to multiply. The original version of this problem, I got a density constant is 2, length is constant at 3, and the width is constant at 5. 2 times 3 is 5, 30 grams. We changed the problem by taking one of those things, the density, and making it variable, and looking at how exactly it changed from left to right. So you could probably see where this is headed. I'm going to make another thing variable. I've got 3 things, density, length, and width. So now I'm going to make density and length variable. So here's our new problem. I'm gonna do the same density, but now we're gonna have a triangle. Oh, that's a rectangle. I forgot my shapes for a second. Seem to be struggling today. Something's wrong with the processor. I don't know if this is a more coffee problem or a less coffee problem, but I do know which solution I'm going to apply. Oh no, is the coffee place closed today? Oh man. So now I'm making two things variable. The density is still 1 plus 0.4 times xi. So I'm using that same density. So at a point, xi units from the y-axis, my density there is 1 plus 0.4 xi. I'm going to use this same density for some small change in x. So that's the dx, or the delta x, is going to be my width again. In this case, the other piece that's variable is the length. So when xi is equal to 0, the length is 3. But as xi increases out to 5, the length drops down to 0. But at this point, xi, I'm also going to have this length which is given by the y coordinates. What we need to do is find an equation for the length as a function of the delta variable x, the same thing we always have to do. And so the length, since we just got this line connecting 0, 3, and 5, 0, we can write a linear function starting off at 3 and decreasing by 3 over 5 units. So a y-intercept of 3 and a slope of -3/5. So the density, sorry, the mass is density times area. And area is going to be length times width. So the mass is going to be the density times the length times the width. We need to break it down like this so that we can replace our constant length with variable length. The density is still 1.1 plus 0.4. The length is 3 minus 3/5 x. The discrete width is delta x. The continuous width is dx. And then we'll integrate over all the x values. And there are pieces of this triangle from x equals 0 to x equals 5. In this case, I skipped the Riemann sum and went directly to The definite integral did not pass go, did not collect $200. Now we could just multiply this out, make this calculation by hand, or said round to 5 significant figures if necessary. So let's just do a calculator thing. I want to math 9, one factor is 1 plus 0.4x. And the other factor is 3 minus fractions, 3/5 in parentheses times x. Close the second factor with respect to x from 0 to 5. Looking at this problem in a vacuum, hard to see if this 12.5 makes sense. But in the context of what we know so far, we know that when we had a rectangle with this same variable density, the mass was 30 grams. And the rectangle is just going to be half the area. But if we look at where most of the area for this rectangle, this triangle is, we've got more light stuff than there is heavy stuff. It's less dense close to the y-axis. Density down here is 1. Density up here is 1 and 0.4 plus 0.4 times 5. So 3. So the density is higher at this end, but there's less material. And so it makes sense that we would have less than half the density of the rectangle. Any questions? DVD bonus material question. How can we get there? The easiest way possible, thinking about how this density is going to operate. How can we get, what would have to change to calculate the mass? So that's what we would want to think about here for this problem. What's the easy way to get at the mass of this triangle? Same density scheme as the previous. What would your instinct tell you is the mass of this triangle? And then how could you set up an integral to check it out? So can't use a length of 3 minus 3/5 x. Still use that same density. One of the things to keep in mind when you're doing problems is that doing 10 problems in a vacuum is where they're all separate, just separate random problems, is less effective than doing 5 problems in a sequence. So you can see the changes. You don't get to play the random access memory game until you play the pattern game. You don't get to see the patterns until you've been through the patterns a piece at a time. Because what's important is not just the individual problems, but the changes in the problems. This is an important thing to think about. Because now we're taking our task, learning math, and not just doing algebra on it. Where are we here? Now do this, now do this, now do this. We're doing the first step in thinking of it in terms of calculus, because it's where are we and how are we changing? Where are we and how are we changing? We're thinking about how things are changing so that we can see where we are. That makes sense? It's like looking at a GPS location and finding coordinates for your cars. It's been stolen. But more important than that, it's also reporting that which direction the car is going. It's not just saying at this moment the car is at point A. It said it's at this moment it's at the point A. That's your function information. And it's headed south at 80 miles per hour. Now you have derivative information as well. That makes sense? Because we're so wired, I don't know if we program this way or if this just comes naturally and that's why we do it. We are programmed to think linearly. That's why we kind of stop at which direction is the thing headed. My car is at this point in this city, headed south at 80 miles per hour. We're not concerned about the next derivative, acceleration. We're not going to say, is the car speeding up or slowing down? We're not really worried about that because we think linearly. In an hour, it's going to be 80 miles south from where it was. Any questions? We're thinking in two derivatives. All right, so this is your problem for today. Same density, but different triangle. What's the easiest answer? How do we get there by subtracting? How is the 30 and the 12.5 going to go into this? How can we think about that? Then let's set up an integral to check that our intuition was correct. All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing. Hopefully I'll be able to source some coffee and get out the fog of weekend.